Hello ladies and gentlemen, this is Mr. Cunningham. What we're going to be talking about today is lesson 12.2, which is over something called the combined gas law. So go ahead and take a few minutes and answer those bell work questions, and then come back and we'll start talking about the combined gas law. Alright, so let's go over our objectives for today. First thing, subobjective 1. You should be able to convert units of pressure, volume, and temperature. Again, that's a continuation from last lesson. Subobjective 2, be able to plug in the correct values for the combined gas law. And our goal, be able to solve for any variable in the combined gas law. So, what we're going to talk about today, again, just rehash some of the relationships that we talked about last lesson. Remember, we talked about pressure and volume, how they were indirectly proportional. If my pressure would go up, my volume is going to go down. That's what indirectly means. Directly proportional is my volume and my temperature. If my volume goes up, if my temperature goes up, my volume is going to go up. Then we talked about pressure and temperature, how they were related. If my temperature increases, my pressure is going to increase because they are directly proportional. Then we talked about our quantity and our volume. Okay? If our number of moles of particles goes up, that means my volume is going to go up. All of those things are going to help us when thinking about this new topic called the combined gas law. So, I got a question for you. Let's say, what happens if I took a balloon from Gas City, from here, and I took it to the top of Pikes Peak. Pikes Peak is in Colorado. It's the top of a mountain. Okay? How is my balloon going to change? Well, think about what changes between here and the top of a mountain in Colorado. Well, temperature is going to change, right? Okay. Pressure is going to change. Okay. Volume is going to change. So we talked about the relationships between, quantity and volume, but what happens when we change a bunch of stuff at the same time, right? In the real world, we don't typically change one thing and hold other things constant because we're not able to, right? What happens if all those things change? What are we supposed to do? Okay, so what happens if we take it to the summit of Pikes Peak? Well, here's the deal, all right? If I have a balloon, all right, and it's in Gas City, there is a relationship between the pressure, the volume, the moles of gas, and the temperature. And those are always going to be equal to a constant, all right? We'll talk about this constant a little bit later. So that is true when in Gas City. But guess what? All of those things are also true when I take a balloon to Pikes Peak. So my pressure, my volume, my moles of gas, and my temperature are all related and they all equal a number. That number that they are equal to is all of these are also equal to that constant when we go to the top of Pikes Peak. Now you might say, well, my pressures aren't going to be the same, my temperatures aren't going to be the same, but they're all, when I multiply them, or when I do my pressure times my volume divided by my moles of gas times my temperature, when I do that in both of these instances, I'm going to get the same value. That's what we call a constant, right? So, here's what that means, okay? If my pressure times my volume divided by my moles of gas times my temperature is equal to this constant, and these two constants are equal to each other, then that means these two things are equal to each other, which gives me this equation. All right? It means the pressure times the volume divided by my moles of gas times my temperature in Gas City is going to be equal to the pressure times the volume divided by my moles of gas times my temperature at Pikes Peak. So if we know enough information, we can solve for the volume. We could solve for the pressure. We could solve for the moles of gas. We could do all that as long as we know the pressure, volume, moles and gas, and temperature of our gas in Gas City or all the way out in Pikes Peak. So, now, what I typically do is we typically plug in ones and twos. What that means is ones stands for, that's what my original conditions were. So originally I had the balloon in Gas City. Then I took the balloon to Pikes Peak. So now that's why we have all these twos. That way we don't get our pressures and our volumes and stuff like that confused because they'd be represented by the same letter. So if my pressure, my pressure, volume, moles of gas, and temperature in Gas City is equal to my pressure times my volume divided by my moles of gas times my temperature at Pikes Peak. Let's say that this is my problem. Let's say that I started with a 3-liter balloon and it was in Gas City or Marion area with a pressure of 0.979 atmospheres, a temperature of 28.5 degrees Celsius, and 2.5 moles of air, and I move it to Pikes Peak, where the temperature is -5 degrees Celsius, the pressure is 0.85 atmospheres, and now I want to know, what is the new volume? So you might be like, what do I do with that? Well, here's what I'm going to do. Okay, I'm going to use this equation, okay, and I'm going to plug in my values. Okay, so let me show you how to do that. So, looking back at my problem, okay, it says I have the balloon started in Marion in Gas City, and it was 3 liters. So, I'm going to have my P1, my V1, over N1 times T1 equals P2, V2 over N2 times T2. Well, did you notice that in the problem, it did not mention, I guess my moles of gas, it says were 2.5. So I'm going to plug in 2.5 there. Did you notice that it did not mention that I let moles of air out? Well, in these types of problems, if it ever doesn't mention that something has changed, we can assume that they are the same thing, which means I still have 2.5 moles of gas. Now, what that also means is if I have the same moles of gas on both sides, I can eliminate that from my equation. Now, if you want to, you can leave these 2.5 moles, these 2.5s in for our moles of gas. You can leave those in. That's fine. All right? What I'm going to do is, just to make the number of calculations I have to do smaller, I'm going to eliminate those amounts. This equation right here is called the combined gas law. It is a relationship between pressure, volume, and temperature when I am changing the location of my container with gas particles in it. So now what I'm going to do is I'm going to go back to my problem, and I'm going to input all of the values that I got. The big thing you need to focus on is, remember, our temperature always has got to be in Kelvin. Also, make sure you don't get mixed up which ones are your original or your P1, V1, and T1. Make sure you keep all of those together. And then your ones that are your secondary, your change, when we took the balloon to Pikes Peak, those are going to be our 2s. All right? So here we go. So it says I had a 3-liter balloon when I started. So I'm going to plug in 3 here for V1. It says my pressure was 0.979. And it said that my temperature was 28.5 degrees Celsius. Now, the thing that you guys are going to want to do is you're going to want to go, oh, 28.5, right? But remember, my temperature has to be in Kelvin. So I cannot use 28.5. I have to go back and use my Celsius to Kelvin conversion. Remember, in order to convert from Celsius to Kelvin, we have to do what? That's right, we have to add 273. So, I'm going to take 28.5 and I get 301.5. Okay, so that's all my initial amounts. Now I'm going to go to my final amounts. So it says it's moved to Pikes Peak, where the temperature is -5 degrees Celsius. Again, I can't plug in -5 there because my temperature has to be in Kelvin when I work with gases. So I'm going to add 273. -5 plus 273 is 268. and it says the pressure is 0.85 atmospheres. That means my P2 is 0.85. Now, you might be like, okay, now I've got my variable, my V2. What is it? Well, that's what it asked us to find. It says, what is the new volume? Well, now I'm just going to solve my equation and get it so that I have V2 by itself on one side and solve it. So, I'm going to solve. Now, you might choose to solve these a variety of ways. I'm going to solve this side first and then do my manipulations on this side. So, I'm going to do 0.979 times 3 divided by 301.5. So, and I get 0.009741. My suggestion for you guys as you do these types of problems is do not round your number until you get to the very final answer. That way you don't end up making a rounding error that could cause you to get it wrong. So now, I'm going to try and, again, still manipulate my equation so I can get V2 by itself. So now I'm going to multiply both sides by 268. Something you guys might choose to do is put this over 1 and do like cross multiplication. You can do that. That's not the way I learned it, so I'm going to do it a different way. So I'm going to multiply both sides by 268. And I get that this is going to be now 2.61067. And it's now going to be equal to 0.85 times V2. Now I'm going to divide both sides by 0.85. So when I divide both sides by 0.85, I get 3.07 liters is equal to V2. Now you might be like, how'd you know that was liters? Here's how you know. Whatever unit you used for volume on this side is the unit that you are going to get on this side. Okay? So I used atmospheres here. Here's what that means. If I get another problem, okay? If I use atmospheres here, I have to use atmospheres here because those are both pressures and they have to be in the same unit. I used 3 liters here for volume, which means this has to be in liters for volume. I used this in Kelvin, which means this has to be in Kelvin. That's another place where some people mess up. All right? So that right here is our answer. In other words, if we took a balloon that was 3 liters from Gas City / Marion, we took it to Pikes Peak under those conditions and we measured them, our balloon would actually grow in size a tiny bit. All right? That's how we can solve mathematically what the size of that balloon would actually be. Okay? So, let's go ahead and try another one. So, suppose you have a tank of oxygen gas containing oxygen at 25 degrees Celsius and 15 atmospheres of pressure. You warm the tank to 35 degrees Celsius and hold the volume constant. Calculate the final pressure in the tank. All right, so let's go ahead and do some calculations here. So, I'm going to read through my problem, plug in my values. So it says you have a tank of oxygen gas and its pressure is 15 atmospheres. So I'm going to plug in 15 for my pressure. And again, that's in atmospheres, which means if I'm going to have pressure on this side, it also needs to be in atmospheres. It says that my, it doesn't mention anything about our volume, so I'm going to plug in V1 here. Then it says that my temperature was 25 degrees Celsius. Well, remember, I can't use Celsius. I have to convert it to Kelvin. So I'm going to do 25 in Celsius plus 273. That gives me 298. That's my temperature in Kelvin. And I'm going to set that equal to, it says calculate the final pressure in the tank. So that means P2, I'm going to put there. That's what I'm going to solve for. Then, here's something that's interesting. It says that my volume is held constant. And you might be like, what does that mean? Why would they tell us that? You want to know what that means? Remember how in the previous problem we talked about how if our moles don't change, we can get rid of them? We can like cancel them out? Same thing happens here. If you ever hold something constant in an equation, that means that my volumes are the same on both sides, which means I can get rid of them. And it says that it warmed my tank to 35 degrees Celsius, which remember, I can't use 35 in Celsius. I have to add 273, which is going to be 308. All right? So now I'm just going to solve this for P2. Okay? Again, you guys might have one way to solve it. I'm just going to, one thing you could do is you could cross multiply here, right? That's possible. I'm not going to do that. I'm just going to solve this side and then multiply by 308 to get my final answer. Again, multiple different ways to solve an equation that are correct. So I'm going to do 15 divided by 298. And I get 0.050336 is equal to P2 divided by 308. So now what I'm going to do is I'm going to multiply both sides by 308. That'll get rid of my 308. So I'm going to take this times 308. And I get 15.50 is equal to P2. Now, what unit is that? You're right, that should be atmospheres. And that's because this 15 here was given to me in atmospheres. So that means I need to put in atmospheres there as my pressure. Now, when you put in responses like on Canvas, you won't include that unit, but it's important that you know what it is. Okay? Let's try one more, then I'll give you guys a chance to try some problems on your own. So our next problem looks like this. It says, at conditions of 785 torr of pressure and 15 degrees Celsius of temperature, a gas occupies a volume of 45.5 milliliters. What will be the volume of the same gas in milliliters at 0.98 atmospheres and 30 degrees Celsius? So let's go ahead and start working on this problem. So again, here's our combined gas law. So let's read through our problem and let's plug some stuff in. So it says that we have a pressure of 785 torr. Okay? It says that my volume is 45.5 milliliters. Oops. There. I'm going to plug in my units for this one. So this is torr. It says my temperature is 15 degrees Celsius. Well, remember, I cannot leave my temperature in Celsius. I need to add 273, which is going to be 288, and that is going to be in Kelvin. I'm going to set that equal to my secondary conditions. It says, what will be the volume in milliliters? Well, that means I'm not going to put in my V2. It says my pressure is 0.98 atmospheres times V2, all divided by my temperature in Kelvin. Remember, it gave me 30 degrees in Celsius, but I have to change that to Kelvin, which is going to be 303 Kelvin. What's the problem with how my equation is set up right now from what we've talked about? What you should have said is that I cannot have units of pressure in different units. They both have to be the same. So it does not matter which one I change, but I need to change one of them. I either need to change atmospheres to torr, or I need to change 785 torr to atmospheres. Doesn't matter which one you choose. I'm going to go ahead and change torr to atmospheres. Remember, in order to do that, I have to know what the conversion between atmospheres and torr is. Well, I know that the conversion between I know that 1 atmosphere is equal to 760 torr, which means I either have to multiply this number by 760 or I need to divide it by 760. Okay, now, what you could set this up in dimensional analysis and know for sure, just to save some time, to change torr to atmospheres, you divide by 760. So I'm going to take 785 and divide by 760. That gives me 1.03289. There, now these are both in atmospheres, these are both in Kelvin, and this is in milliliters. Now you might be like, do I need to change that to liters? Well, in fact, that would actually be a bad idea. Here's why. Notice that the problem says, what will be the volume of the same gas in milliliters? If I change this to liters, that would mean it would give me my volume in liters. I don't want that. I want it to be in milliliters. So if I have my volume here in milliliters, that means my unit that is that I solve for when I get my V2, when I get that number, that unit is going to be in milliliters. So I actually want to leave this in milliliters. So let's go ahead and solve this. So I'm going to do this number times 45.5 divided by 288. Again, there are multiple correct ways to solve this. I'm going to just solve this side of the equation first. Again, I encourage you with these calculations to work through them as I do so that you can check and see if you're doing them correctly. Now I'm going to multiply both sides by 303 to get rid of the 303 on this side. Now I'm going to divide both sides by 0.98. That way I can get rid of 0.98 on this side. And here's where I can round. So what I get is that my volume, my V2, should be equal to 50.45. And you might say, well, what unit is it? Again, since I use milliliters here, that means my unit that will be for V2 is also in milliliters. So that answers my question because it specifically asked me, it said, what is the volume in milliliters? Okay? So what I want you guys to do is go ahead and give this next problem a try. All right? I want you to give it a shot. You'll put in an answer. Then what I will do is I will go through and show you how I work through the problem. So here's that question. It says, what's the volume occupied by a gas at 2 atmospheres and 200 Kelvin if a container originally had 2.5 moles of gas with a volume of 300 liters at 0.25 atmospheres and 400 Kelvin? Go ahead, give that problem a try, and then come back here and we'll work through it. Okay, so let's work through this problem. So, it says, what is the volume occupied by a gas at 2 atmospheres and 200 Kelvin if the container originally had 2.5 moles of gas with a volume of 300 liters at 0.25 atmospheres and 400 Kelvin. So, what's weird about this problem is they give you the final stuff first. All right, because it says if a container originally had this many moles, had this volume, had this pressure, had this temperature. So actually, the stuff at the end of our problem is actually our initial stuff. So we have initially 2.5 moles. Now you might go, well, there's no moles up here. The nice thing is if it doesn't mention that moles change, remember, if moles don't change, we drop them out. So since no moles changed, that 2.5 moles is actually just there to kind of try and throw you off. You don't need it. So I'm going to skip over the 2.5 moles because it's unnecessary. But it does say the volume is 300 liters. So I'm going to plug that in for V1. My pressure is 0.25 atmospheres, so I'm going to plug that in for P1. And it says that my temperature was originally 400 Kelvin. And I'm going to set that equal to the stuff that it gave me at the beginning of the problem. So it says the volume was, what is the volume occupied by a gas at 2 atmospheres? So now my pressure is 2 atmospheres. I don't know the volume. And my temperature is now 200 Kelvin. And now I'm going to solve for V2. So I got 0.25 times 300 divided by 400. And I get this side of the equation is going to be equal to 0.1875. And so that's going to be equal to 2 times V2 all over 200. So I'm going to multiply by 200 on this side. And again, when I multiply by 200 on this side, I'm technically also doing that over here, right? Times 200, but I'm canceling those out because they're going to end up kind of negating each other. So times 200, I get 37.5 is equal to 2 times V2. Now I divide both sides by 2. And I get 18.75. And what is that unit? Again, since I used liters here, that means this also has to be liters. And that is equal to my volume. Okay, that ends our lesson over the combined gas law. So what I want you to do now is take some time to answer these questions at the end of your notes. Again, answer those. It will give you the correct answers after you respond and put in your question, put in your answer. If you have any questions for me, please make sure you don't hesitate to ask. This can be difficult stuff, just like anything we do, but make sure you're utilizing me. I'll make sure you're showing your work very similar to what I do. That way I can look through your problem and hopefully help you find your mistake. Well, thank you for watching.